Welcome to Sleepy Space Facts, where questions drift as softly as starlight. Tonight we ask one of the quietest yet deepest mysteries. Did nothing ever exist? Not the stars, not the planets, not even the faintest whisper of light, just pure nothing. Settle in, relax your body, and let us wander gently into the void. We'll take it slow with soft voices and a calming curiosity. After all, this isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. Now, I do hope the video isn't too interesting. That would be terribly inconvenient at bedtime. But if it happens to keep your mind gently glowing, well, at least you'll be learning something fascinating while you drift. Before we begin our cosmic wandering, I'd love it if you tapped the like button. And if you enjoy gentle science journeys like this, feel free to subscribe. It helps more curious souls find their way here. Let me know in the comments where in the world you're watching from and what time it is for you right now. Is it just past midnight or the early glow of 4 a.m.? I always love reading those sleepy check-ins. And finally, while we're going to explore some deep and dreamy questions tonight, please remember, this is not medical advice, just a soft place to land at the end of your day. Let's begin. Let's take a deep breath. Not to fill your lungs with cosmic insight just yet, but because we're about to dive into a subject that seems simple at first, but quickly becomes slipperier than a bar of soap in a black hole. Tonight's question is, what do we really mean by nothing? You'd think that of all the things in the universe, in or outside of it, nothing would be the easiest to explain. After all, it's, well, nothing. No things, no stuff, just emptiness, right? But here's where it gets interesting. The more carefully we examine nothing, the more it starts to look suspiciously like something. And as we'll see, in both science and philosophy, nothing can wear quite a few disguises. In fact, there are several kinds of nothing, each one stranger and more counterintuitive than the last. Let's start small with something familiar. Picture an empty jar sitting on your kitchen counter. You screw off the lid and look inside. It appears empty. There's no peanut butter, no sugar cubes, not even a lone grain of rice. Most people would call that nothing. But of course, that's not quite right. The jar is full of air, oxygen, nitrogen, a bit of carbon dioxide, maybe the lingering scent of cinnamon from whatever it held last week. Molecules are bouncing around in there like invisible popcorn. If you were an ant with a chemistry degree, you'd be overwhelmed by just how not nothing it really is. Okay, let's step it up a notch. What if we suck all the air out of the jar, vacuum seal it until there's no atmosphere left inside at all? Now we've got a vacuum, or what we might call empty space. Is that nothing? Well, we're getting closer. But even this vacuum isn't truly empty. First, there are still fields inside. Not cornfields, but the invisible kind that exist everywhere in the universe. These are quantum fields, and according to modern physics, they can never be completely turned off. Even in their lowest energy state, they still ripple with possibility. And this is where things start to get quantum weird. In the early 20th century, scientists like Max Planck and Vera Heisenberg discovered that the tiniest levels of nature are never truly still. Even a perfect vacuum devoid of matter, and energy is still humming with uncertainty. Tiny particles pop into and out of existence constantly. They're called virtual particles, and they're part of what physicists call quantum fluctuations. In other words, even nothing is always doing something. Imagine your empty jar again. If we could make it truly vacuum sealed, removing every molecule of air and then shrank ourselves down to the quantum scale, we'd still see things happening, not because matter is leaking in, but because the fabric of the universe itself is restless. It fizzes with energy. The vacuum is like a quiet ocean that looks calm from above, but teems with life below the surface. So here we are, two versions of nothing down, and neither one is truly empty. Let's take it further. What if we removed space itself? Not just the stuff in space, but space itself gone. No dimensions, no up or down, no left, no right. Can we even imagine that? This is where language starts to fail us. Without space, we can't describe where anything is, or even where nothing could be. It's not a black void. It's not a white screen. It's not darkness, silence, or emptiness. It's the absence of place itself. You can't put your mind inside it because there's no inside. Then let's get even more radical. What if we took away time as well? No seconds ticking by, no change, no motion. A timeless, spaceless, matterless what? Some physicists and philosophers propose that this is the only true form of nothing, the absolute absence of everything, including the dimensions in which things can exist or happen. But now we're dealing with something almost paradoxical. If there's no space or time, can we even say it exists? And if it doesn't exist, then what is it? It's a bit like trying to draw a square circle. The words make sense individually, but together they become nonsense. In the same way, our brains, which evolved to track fruit, faces, and predator footprints, aren't naturally equipped to visualize the absence of all things. Nothing in its most extreme definition might be not just beyond our senses, but beyond thought itself. Of course, some philosophers have argued that nothing doesn't make sense at all, that it's a concept invented by language. When we say something is not there, like when your friend says there's nothing in the fridge, we still mean something. We mean the fridge is present, just empty of the items we want. But when we talk about absolute nothingness, we're using words that point to an absence we've never encountered. Heidegger, the famously cryptic German philosopher, once asked, "Why is there something rather than nothing?" It's one of those questions that sounds obvious at first, but grows more unsettling the longer you think about it. And the more we learn from science, the more it seems that nothing might not just be hard to find. It might not exist at all. Even the term before the Big Bang may already be a kind of error. If time began with the universe, then asking what came before is like asking, what's north of the North Pole? The question seems to make sense, but collapses under its own logic. Still, it's a very human question. We crave origin stories. We like to trace things back. Family trees, historical timelines, the last slice of cake. But when it comes to the universe, we may hit a wall, a soft, baffling, quantum fluctuating wall. So where does that leave us? It leaves us with several kinds of nothing, all of which are actually quite something. From airless jars to seething quantum vacuums to theoretical voids outside of space and time, nothing is not one neat concept. It's a spectrum of increasingly abstract possibilities, and in the end, we might have to accept that pure total nothingness may not be part of reality at all, only part of our imagination. But that doesn't mean the question is pointless. Quite the opposite. Asking what nothing is helps us understand what something really means. It's in the contrast that clarity emerges, or at least a kind of peaceful confusion. And as we'll see when we explore the origin of the universe, nothing may be not the end of the line, but the beginning of a very strange road. So, let's keep floating gently through the questions. There's a lot of nothing left to uncover. Let's take a gentle step forward, or maybe backward, depending on how you think about time. We're going to take a calm stroll through the history of, well, everything. But don't worry, you won't need a time machine or a seatbelt. Just a quiet mind, a comfortable pillow, and perhaps a sense of cosmic wonder. Tonight, we're visiting the moment the universe began, or at least the moment our current understanding says it did. This is the story of the Big Bang, not a loud explosion in space, despite the dramatic name, but a gentle unraveling of space itself. A moment so strange that it gave birth to not only everything we see, but the very space and time in which we see it. Let's imagine you're standing in the deepest corner of space, far from any stars or galaxies. There's no sound, no breeze, just the soft hum of distant starlight and the feeling of cosmic stillness. That stillness, though, hides a secret, because everything, all the planets, stars, galaxies, and even the emptiness between them is moving apart. Slowly, gently, and inevitably, space itself is stretching. This idea that the universe is expanding was one of the great revelations of the 20th century. For a long time, scientists assumed the cosmos was static, fixed, eternal, unchanging. But then, in the 1920s, a Belgian priest and physicist named Giora Lamed had a very curious idea. What if the universe was not static, but expanding outward from a single dense point? Around the same time, American astronomer Edwin Hubble was peering through his telescope and making an equally curious observation. The light from distant galaxies wasn't just dim, it was redder than expected. Not because they were embarrassed, but because they were moving away from us. This shift in wavelength, known as redshift, was a cosmic clue. It meant space was stretching and everything in it was being carried along like raisins in a rising loaf of bread. And if everything was moving apart, then it must have once been much closer together. Imagine rewinding the universe like a film played in reverse. Galaxies rushing toward each other, stars condensing, matter folding inward, all collapsing into a tighter and tighter ball until about 13.8 billion years ago. You reach a moment of unimaginable density and temperature, a kind of cosmic seed, a singularity, as it's sometimes called. Not a thing inside space, but the point at which space itself began. This is what we call the Big Bang. It wasn't an explosion in space. There was no pre-existing vacuum, no cosmic firework lighting up a black sky. Instead, it was the sudden dramatic expansion of space itself, the birth of time, energy, and the laws of physics as we know them. And no matter where you stand in the universe, it looks like everything is expanding away from you. Not because you're special, but because space itself is growing in all directions. It's a bit like dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from the others. Not because they're traveling across the surface, but because the surface itself is expanding. That's our universe, a balloon of space-time slowly inflating for billions of years. Now, what actually happened in the first moments of this expansion? That's where things get delightfully complex. In the tiniest fractions of a second after the Big Bang, and we're talking trillionths of a trillionth of a second, the universe was a hot, dense plasma of particles and energy. Temperatures were so high that matter couldn't exist in the forms we recognize. Protons and neutrons hadn't formed yet. Even atoms were still a future luxury. Everything was a glowing soup of fundamental ingredients. But as the universe expanded, it also cooled. That cooling allowed energy to condense into particles. Quarks began to combine into protons and neutrons. After a few minutes, these joined to form the first simple nuclei, mostly hydrogen and a little helium. Fast forward a few 100,000 years, a blink by cosmic standards, and the universe had cooled enough for electrons to settle into orbits around nuclei. For the first time, neutral atoms formed, and something beautiful happened. Light, which had been bouncing off free particles like a strobe in a foggy room, could finally travel freely. This moment, when the universe became transparent, left behind a whisper, a kind of soft, ancient glow still visible today. It's called the cosmic microwave background, or CMB for short, and it's one of the strongest pieces of evidence we have for the Big Bang. The CMB is everywhere. It fills the universe with a faint, nearly uniform microwave signal. It's not strong. You'd need a very sensitive antenna to detect it, but it's there, like a baby picture of the cosmos, frozen in time. Tiny temperature fluctuations in this ancient light give us clues about the earlier structures, the seeds of galaxies, stars, and planets. Discovered in the 1960s, almost by accident, by two radio astronomers, Arno Penzias and Robert Wilson, the CMB was a game changer. They thought the static they were hearing was from pigeon droppings on their antenna. It turned out to be the echo of creation. But even with all this evidence, the redshift of galaxies, the cosmic microwave background, the proportions of light elements, the Big Bang model doesn't answer everything. In fact, it raises some tantalizing questions. For instance, what exactly caused the Big Bang? What triggered that initial expansion? Why did the universe begin in such a low entropy, highly ordered state? A state seemingly fine-tuned for complexity and life. And of course, the big one. What came before the Big Bang? That's the question that brings us full circle. Because if the Big Bang was the beginning of time and space, then before might not even exist. There may not have been a before to speak of, only an origin point from which everything else flowed. Still, not everyone is satisfied with that answer. Some physicists propose models in which the Big Bang was not the beginning, but a transition, a bounce, a cycle, or the birth of one universe among many in a vast multiverse. We'll explore all of those possibilities in the chapters ahead. But for now, we sit gently with the Big Bang, not as a noisy explosion, but as the quiet, powerful unfolding of everything. A beginning not in fire, but in form. Not in a bang, but in a breath. The breath of space itself. If you've ever found yourself staring up at the stars and wondering where it all began, you're not alone. Humans have been asking that question since long before telescopes, spaceships, or glow-in-the-dark ceiling stickers. It's a deeply natural instinct to seek origins, to trace back the thread of time as far as it will go. And when we follow that thread all the way to the edge, we arrive at a curious place. A place where time itself may have had a birthday. Now, let's pause here and let the idea settle gently. The beginning of time, not just the beginning of the universe or of stars or atoms or coffee, but of time itself. It's a bit like finding out that your watch didn't just stop working, but actually cease to have any reason to exist before a certain moment. To explain what this really means, we need to go back to the Big Bang, or more precisely, the Big Beginning. In the standard model of cosmology, space and time are not separate entities. They're part of the same stretchy dynamic fabric called spacetime. Think of it as a vast invisible trampoline, and everything in the universe, from dust particles to galaxies, sits and moves atop its surface. According to Einstein's general theory of relativity, this fabric can warp, bend, and stretch in response to mass and energy. That's what we experience as gravity. But here's the truly bizarre part. That same fabric also has a beginning. And that beginning, as far as we can tell, is the Big Bang. This means that space didn't explode into some pre-existing void. Rather, space itself was created in that moment. And because time is part of the same fabric, it too came into being. There was no ticking clock before the bang, no empty hallway waiting to be filled, no before, because there was no time in which a before could exist. It's an idea that defies our usual instincts. In our everyday lives, everything has a before. Before breakfast, there was sleep. Before sleep, there was brushing your teeth. Before that, probably some late-night snack you're not proud of. We are deeply conditioned to think in terms of linear cause and effect. So when someone says time had a beginning, it's tempting to say yes, yes, but what was before that? And that's where the gently absurd analogy comes in. Asking what happened before time began is like asking what's north of the North Pole. The North Pole is the top of the world. It's not just a very cold place with polar bears and the occasional elf workshop. It's the furthest north you can go. Try walking north from there and you'll just start heading south. In the same way, time reaches a kind of boundary at the Big Bang. It's not that something was hiding behind it. It's just that the concept of before loses its meaning. In fact, many physicists describe the Big Bang not as a moment in time, but as the moment when time itself became meaningful. Before that, if we can even say before, there may have been no flow of time at all, just a timeless, spaceless state outside the bounds of our physics. It's a bit like asking what your phone battery was doing before it was manufactured. It didn't exist yet. There was no function, no capacity, no timekeeping. Only after the phone is assembled, charged, and powered on can it start ticking and notifying you about emails you'll probably ignore. Similarly, the universe may have been unpowered, so to speak, until the Big Bang flipped the switch. And with that flip came time, space, energy, and all the cosmic ingredients that followed. Of course, this raises a different kind of question. If time began at the Big Bang, what caused the Big Bang? Doesn't a cause require time to precede effects? You're not alone in asking that. It's one of the slipperiest concepts in all of physics. Most cause and effect relationships we know depend on time flowing forward. You toss a ball, then it flies. You pour tea, then it fills the cup. But if the universe began in a timeless state, the normal rules don't seem to apply. Some physicists speculate that the cause of the Big Bang may not be a cause in time, but a kind of boundary condition, a set of starting rules that simply are, like a board game that springs into being with the dice already in motion. There is no first player, because the rules themselves begin the game. And here's another twist. Not all physicists even agreed that time had a sharp beginning. Some models suggest that time may be more like a loop or a bounce, contracting and expanding in cycles with no true beginning or end. We'll visit those ideas later on when we explore theories like the Big Bounce and loop quantum cosmology. But for now, let's stay with this strange but simple notion that time had a beginning, that it emerged from the Big Bang just like light, matter, and motion. That before the universe, there wasn't a clock ticking in a dark room waiting for someone to press start. It's hard to wrap our heads around because our heads evolved to keep track of days and seasons. Not the curvature of spaced email, but in some ways, it's a liberating idea. If time had a birthday, then every second that exists, including this one right now, is part of a grand unfolding. A story that began 13.8 billion years ago and is still being written. And perhaps most remarkably, every moment we experience is layered within that cosmic timeline. The ticking of your heartbeat, the flicker of neurons in your brain, the soft rustle of your bedsheets, all of it part of time's fabric, a fabric that, according to our best understanding, didn't always exist. So the next time someone casually asks you what happened before the Big Bang, you can smile sleepily and say, "That's like asking what's north of the North Pole." Then you can sip your tea and drift into the kind of dream only the universe itself could imagine, because time, like a river, had a source. And for reasons we may never fully grasp, that source seems to have emerged not within time, but instead alongside it. Time had a beginning, and here we are floating in its current dot. The Big Bang, it's one of those names that sticks in the mind. Punchy, dramatic, and wonderfully explosive. It conjures up images of a dark, empty void suddenly lit up by a colossal boom. Like the universe was born from the finale of a cosmic fireworks show. But as it turns out, the name Big Bang might be one of the most misleading titles in the history of science. And understanding why can help us see the origins of the universe and the idea of nothing before in a very different light. Let's start with a little historical trivia, because it's oddly fitting. The term Big Bang was actually coined as a joke. Back in the 1940s, a brilliant but skeptical British astronomer named Fred Hoyle used the phrase during a BBC radio broadcast. Hoyle didn't believe in the idea of a universe with a beginning. He was a champion of the rival theory at the time, the steady-state model, which suggested that the universe had always existed and was constantly generating new matter as it expanded. So when Hoyle sarcastically referred to the competing idea as the Big Bang, he meant it as a jab, a flippant nickname for what he thought was a silly, unscientific concept. The name stuck. The theory did too. Ironically, the evidence piled up in favor of the Big Bang model, and poor Fred Hoyle became eternally linked to a theory he didn't believe in, all because of a throwaway line on the radio. But let's be clear, despite the name, there was no bang, at least not in the way we usually think of one. An explosion in the everyday sense happens in space. A firework goes off in the sky, sending sparks outward through the air. A volcano erupts, hurling ash and lava across the land. These are loud, violent events that happen at a specific location with debris flying outward into a larger background. But the Big Bang was not like that. The Big Bang wasn't an explosion in space. It was an expansion of space. That difference might seem subtle, but it's everything. Imagine blowing up a balloon. You take a red marker and draw little dots all over its surface. These dots represent galaxies. As you inflate the balloon, you'll notice that the dots move away from each other, not because they're crawling across the rubber. They're fixed in place, but because the surface itself is stretching. Every bit of balloon is getting bigger, and that's carrying the dots apart. That's what the universe is doing. Galaxies aren't flying apart through some vast emptiness. Space itself is expanding. The distances between galaxies grow because the fabric of the cosmos is stretching. The balloon gets bigger, so everything on it gets farther apart. And here's the key part. The balloon doesn't have a center. Every point is moving away from every other point. There's no central explosion site. If you're standing on any one of those dots, it looks like you're at the center with everything else rushing away. But that's just an illusion caused by uniform expansion. Our universe works in the same way. No matter where you are, you'll see galaxies receding in all directions. It gives the impression that you're at the center of the bang, but so does every other galaxy. There is no center. There is no edge, just a boundless stretching space-time. Now, let's gently rewind the balloon. If we shrink it back in time, the dots get closer together. The surface contracts. The balloon tightens down until at some finite point in the past it reaches a state of extreme density and temperature. A tiny, hot, uniform thing. That's our starting point. But remember, in this analogy, the balloon's surface is space itself. So, when we rewind to that tightly packed state, we're not zooming in on an object in space. We're zooming in on the very fabric of space and time, becoming smaller, denser, hotter, and eventually reaching a state where our current physics breaks down. In other words, the Big Bang wasn't something that happened inside the universe. It's the moment the universe, and with it, space and time, came into being. Which brings us back to the idea of nothing. Because if the Big Bang wasn't an explosion in pre-existing space, then there wasn't a waiting emptiness for it to happen. There wasn't a cold, dark stage sitting patiently for a universe to show up and start the show. There was no container, no backdrop, no space at all. This changes everything about how we think of beginnings. In our daily lives, we expect everything to unfold in time within a space. But the Big Bang suggests that time and space are part of the thing that began, asking what came before it or where it happened. Maybe like asking what's outside of the canvas in a painting that is the canvas. If space is expanding, then going back in time means space is shrinking. And if time itself is part of that story, then there may not have been a before in the way we usually think of it. Not because we're missing information, but because the very concept might not apply. To go back to our balloon, imagine trying to peel off the rubber and ask what's underneath the surface. But the balloon doesn't exist in three-dimensional space. In this analogy, the surface is all there is. Asking what's underneath is a category error. This is why physicists tread carefully when talking about what preceded the Big Bang. Some propose that the question is meaningless, like asking what's north of the North Pole. Others think it points to a deeper mystery, that our current models are incomplete, and some new theory of quantum gravity might give us a window into a before we can't yet describe. But one thing's for sure, calling it a bang sets up the wrong mental picture. There was no shrapnel, no debris, no sonic boom echoing through a void. There was no there. What we got was the unfolding of everything. An expansion of space-time itself from an origin point we don't fully understand. It was quiet. It was smooth. It was mathematically precise. And yet, it created everything from the stars in the sky to the atoms in your fingertips. Galaxies, photons, black holes, Beethoven, banana bread. All of it has roots in that unfathomable moment when space took its first breath. So, the next time someone talks about the Big Bang, as if it were a loud cosmic detonation, feel free to smile knowingly and gently suggest that it might have been more of a big stretch. A calm, expansive beginning that left behind not a crater, but a universe. And in that stretching silence, we find not just a new way of seeing the cosmos, but a deeper understanding of what it means for nothing to become everything. Picture the quietest place you can imagine. Maybe a dark, empty room with thick walls and no windows, no ticking clocks, no rustling wind, not even the hum of electricity. A pure, perfect silence. Now zoom out, way out, until that room becomes a patch of outer space, light years from the nearest star. No dust, no radiation, no planets or particles. You'd be forgiven for thinking you've arrived at true nothingness. But in the quantum world, even that kind of stillness is a noisy place. Tonight, we're going to take a slow, curious dive into one of the strangest ideas in all of physics. The idea that empty space isn't actually empty. That even in the absence of all matter and light, the vacuum itself is brimming with invisible activity. A restless sea of possibility known as quantum fluctuations. To understand this idea, we need to visit a concept that underpins much of modern physics, quantum field theory, or QFT for short. It might sound intimidating, but we'll take it gently, step by step. In classical physics, the kind you might remember from school, the world is made of particles, tiny little billiard balls that move around in space, collide, bounce, and occasionally break into pieces. Light, for example, was once thought of as a wave, while matter was seen as particles. But quantum theory showed us that reality is far more complicated and far more elegant. Quantum field theory tells us that everything, every particle, every force is a ripple in a field. Imagine the universe as a vast ocean, but not of water. Instead, this ocean is made up of fields, invisible layers of energy that stretch across all of space. There's a field for electrons, a field for quarks, a field for photons, even a field for the Higgs boson. These fields aren't confined to specific locations. They exist everywhere, all the time. Now, here's the magical part. When a field vibrates in just the right way, it produces what we see as a particle. An electron is just a ripple in the electron field. A photon, a ripple in the electromagnetic field. It's like throwing a stone into a pond and watching the waves spread out. Only in this case, the ripple is the stone. But even when the pond seems perfectly still, no ripples, no wind, there's still energy. At the quantum level, fields are never truly at rest. They wiggle spontaneously due to the strange rules of uncertainty that govern the quantum world. This is where quantum fluctuations come in. According to the Heisenberg uncertainty principle, there's a limit to how precisely we can know both the energy and the timing of events. This means that even in a vacuum where there are no particles and no radiation, energy can temporarily spike. For the briefest moments, particles can flicker into existence and then disappear again. These are called virtual particles, and while they're not directly observable in the way normal particles are, their effects can be measured. It's a bit like borrowing a cup of sugar from your neighbor and returning. It's so fast they don't even notice you were there. Except you're a pair of subatomic particles, and your neighbor is the universe. So when we say the vacuum isn't empty, we don't mean it's secretly full of stuff. We mean that even in its lowest energy state, space is still humming with jittery temporary excitations. These fluctuations are incredibly brief and small, but they are real. Real enough to have measurable consequences. For instance, quantum fluctuations can shift the energy levels of electrons in atoms, a phenomenon known as the Lamb shift. They can cause forces to emerge between uncharged metal plates placed very close together in what's known as the Casimir effect. And they may even be responsible for some of the randomness that underlies radioactive decay. But here's where things get really fascinating and relevant to our larger question. Could this fluctuating, jittery vacuum be the true origin of our universe? Some physicists think it might be. Let's drift into the idea slowly. If space can never be truly empty, and if quantum fluctuations are always bubbling beneath the surface, then maybe, just maybe, a A fluctuation of the right kind could cause something big to happen, something like the birth of a universe. One proposal suggested by physicist Alexander Valenkin is that the universe could have tunneled into existence from nothing. Not nothing in the philosophical sense, but a kind of quantum nothing. A state with no classical space or time, but with the potential to fluctuate due to quantum uncertainty. In this view, the universe wasn't caused by anything in the traditional sense. It didn't explode out of a pre-existing space or emerge from a deity's command. Instead, it could have spontaneously appeared, a quantum fluctuation on a cosmic scale, allowed by the rules of quantum mechanics. To be clear, this isn't magic. It's not a loophole. In the quantum world, spontaneous events with non-zero probability can and do happen. It's just that most of them are tiny and fleeting. But if the conditions are right, if the vacuum has enough energy, for example, a fluctuation could trigger inflation, the rapid expansion that set the stage for the Big Bang as we know it. In this sense, the universe may have emerged from a vacuum state. Not an absolute nothing, but a seething dynamic field of potential. The kind of nothing that's actually quite something. Now, some of you might be thinking, wait, doesn't this still leave us with something? Where did the quantum fields come from in the first place? And that's a fair question. This approach may push the mystery back a level, but it doesn't erase it. If quantum fields are eternal, then we're no longer asking where the universe came from, but why these fields exist at all. If they're not eternal, then we're back to wondering what gave rise to them. But the beauty of this idea, this quantum vacuum, is that it shows us a possible bridge between nothing and something. It blurs the boundary. It hints that what we used to think of as nothing, a silent void, may be the very stage on which existence performs its quietest, strangest magic. And it makes sense in a way that the universe would be born not from a bang, but from a ripple, a flutter in the stillness, a whisper in the dark. So, as you lie there letting your thoughts drift like let's imagine just for a moment the quietest silence possible. A silence not just without sound, but without time. Not just without motion, but without space. No stars, no atoms, no energy, no past, no future. Not even a black void. Just the absence of everything. And then a universe. This might sound like the setup for a bedtime fairy tale. Once upon a time, there was no time. But in the curious world of theoretical physics, it's more than a bedtime story. It's a serious attempt to understand how everything could have emerged from what we once called nothing. Tonight, we're going to float gently into one of the boldest ideas in modern cosmology, the notion that the universe could have quantum tunneled into existence. A model proposed by physicist Alexander Valenkin and others, where reality itself flickered into being not from a divine command or a fiery explosion, but from a quiet quantum possibility. Now, before we tiptoe into tunneling, let's revisit something we learned in the last chapter. The vacuum is never truly empty. Even the calmest space bubbles with quantum fluctuations, little borrowings of energy that vanish as quickly as they appear. This is because of the strange logic of the quantum world, where things that are forbidden in classical physics can still happen as long as they don't last too long. And this idea that nature has some flexibility, a kind of quantum wiggle room, brings us to quantum tunneling. In classical physics, if you throw a ball at a wall and it doesn't have enough energy to get over the top, it will just bounce back. That's it, game over. But in quantum physics, there's a chance, a small but real one, that the ball could simply appear on the other side of the wall. not because it jumped over or tunneled through in the usual sense, but because particles aren't like tiny marbles. They're like waves, fuzzy, probabilistic, slightly mischievous waves. And sometimes those waves allow things to appear where they shouldn't be allowed according to our everyday expectations. This phenomenon, known as quantum tunneling, is not just theory. It's been observed in countless experiments. It's how nuclear fusion happens in stars. It's how some particles decay. And it might just be how the universe was born. So, how does that work? Let's ease into Alexander Vilenkin's idea, one of the most quietly radical ideas in all of cosmology. In the early 1980s, Vilenkin proposed that the universe could have tunneled into existence from a state with no classical space, no time, and no matter. In other words, from nothing. But this wasn't an ordinary nothing. It wasn't empty space. It wasn't a vacuum waiting to be filled. It was the absence of all physical structure, yet somehow still governed by the rules of quantum physics. This sounds strange, and it is. But remember, quantum physics allows for possibilities that defy classical intuition in Vilenkin's model. The universe didn't need a cause in the traditional sense. There was no ticking clock before it, no spatial coordinates to mark its arrival. Instead, it was like a particle appearing on the other side of an impossibly high wall. Not because it climbed over, but because the laws of quantum mechanics gave it a tiny but non-zero chance to exist there. This is sometimes called quantum cosmogenesis, the birth of a cosmos through quantum means, and it comes with a remarkable feature. The probability of tunneling is related to the energy of the resulting universe. That is, smaller, simpler universes are more likely to tunnel into existence than larger or more complicated ones. Now, if you're wondering, wait, how can quantum laws exist in a place with no space or time? You're not alone. It's a delicate philosophical and scientific question. Some physicists argue that quantum laws are so fundamental they don't need a pre-existing universe to operate. They're not like traffic rules written on signs. They're more like the blueprint of possibility itself. You can think of it like this. Even if there is no game board yet, the rules of chess still exist conceptually. And once the board appears, those rules dictate how pieces can move. Similarly, the pre-universe nothing in Vilenkin's model doesn't have a game board, no space-time, no geometry, but it may still be shaped by quantum rules that determine what can happen and how likely it is to happen. And according to this idea, what can happen is astonishing. An entire universe complete with its own space, time, energy, and physical laws can tunnel into being, and we might be living in it. So where does this leave us in our journey to understand nothing? Well, it shifts the question a bit. In Vilenkin's model, there may be no before the universe in the traditional sense, but there is a mathematical space of possibility described by quantum laws. The nothingness isn't an empty box. It's more like a potential, a kind of seedbed of realities that could bloom, given the right moment, or perhaps more accurately, given the right absence of moments, since time itself doesn't yet exist in this state. This idea that universe as a spontaneous probabilistic event might feel strange or even a little unsatisfying. We're used to thinking of causes. Things happen because of something else. But in the quantum world, some events don't need causes in the usual sense. They're allowed to happen by the rules of probability, not by the rules of determinism. And what's especially lovely about Vilenkin's model is that it doesn't require any exotic ingredients. No mysterious pre-existing space, no divine spark. Just quantum mechanics doing what it always does, allowing unlikely things to happen given enough time, or in this case, giving birth to time itself. Of course, this is still speculative. No one has a telescope powerful enough to peer before the Big Bang or into the quantum fuzz that may have preceded it. These are ideas grounded in mathematics and theory, not direct observation, but they offer a tantalizing glimpse at how the universe might have emerged not in a bang, but in a whisper of possibility becoming reality. And here's a little bonus twist. Because quantum mechanics is symmetric in time, there are models where the universe doesn't just tunnel forward into existence. It might tunnel symmetrically with two time directions emerging from the same starting point. That is, there could be a mirror universe expanding in the opposite direction in time from ours. Don't worry, you won't meet your backward self at the grocery store. But it's another example of how strange, elegant, and mysterious the quantum origin of the universe might be. So, could quantum tunneling from nothing be the answer to how everything began? Possibly. It's one of the best guesses we have. And it's a gentle, profound idea that the entire cosmos may have started as a tiny chance event born from a rulebook that doesn't need a referee or even a field to play on. It's humbling. It's mind-bending. And it's strangely soothing. From nothing, or almost nothing, came everything. Not with a bang, but with a quantum shrug. Let's take a quiet pause, a deep breath in the darkness, and go back again. Not just to the beginning of the universe as we know it, but just before that. To a moment so brief and mysterious that it makes the blink of an eye look like an eternity. We're entering the era of cosmic inflation, a silent boom that may have laid the groundwork for the Big Bang. It's one of the most astonishing concepts in modern cosmology, and it helps answer some puzzling questions about the universe's shape, temperature, and structure. But it also opens up some new ones, including what made the universe inflate in the first place, and what was there before that. To explore this, let's start with a curious observation, one that puzzled cosmologists for decades. When we look out into the night sky with our most sensitive instruments, we see that the universe is remarkably uniform. The temperature of the cosmic microwave background, the ancient light from the early universe, is nearly the same in every direction. We're talking about differences of less than 1 part in 100,000. That's an astonishing level of smoothness. But here's the riddle. Regions of space that are currently so far apart that they could never have interacted, even at the speed of light, somehow ended up with nearly identical properties. It's like baking 2 loaves of bread on opposite sides of the solar system and finding out they rose at exactly the same rate with the same number of air bubbles and the same golden crust. How did they know to behave the same way? This is called the horizon problem, and it's one of several issues that the original Big Bang model couldn't explain on its own. There's also the flatness problem, the observation that the universe appears to be geometrically flat, meaning parallel lines stay parallel over vast distances. For this to be the case, the early universe would have needed to be balanced with extraordinary precision between expansion and gravity. Even the tiniest deviation in density would have led to a very different cosmos, either rapidly collapsing back in on itself or expanding too quickly for galaxies to form. And finally, there's the monopole problem. Not the board game, but the prediction from early physics theories that heavy magnetic monopoles should have been produced in abundance during the high-energy early universe. Yet, we've never found a single one. These problems seemed like clues, hints that something important was missing from our understanding of the universe's earliest moments. Enter inflation. In the early 1980s, a physicist named Alan Guth proposed a radical idea. What if, just after the birth of the universe, perhaps even at the very moment of its emergence, space underwent a brief period of exponential expansion, not just growing steadily, but doubling in size again and again, faster than the speed of light for a tiny fraction of a second. This is the theory of cosmic inflation, and it changed everything. According to inflation, the universe expanded by an incredible factor, perhaps by a 100 trillion times in less than a trillionth of a second. That's not just fast. That's almost unimaginably fast. But because it happened so early and ended so quickly, it didn't break any physical laws. In fact, Einstein's theory of relativity allows space itself to expand faster than light. It's only objects within space that are bound by that speed limit. So what does inflation do for us? Well, it solves the horizon problem neatly. If all the matter and energy in the universe were originally packed into a tiny region, so small that it could come into thermal equilibrium, then inflation would have taken that tiny uniform patch and blown it up to cosmic size. That's why we see such smoothness across vast regions of space today. They were once close enough to communicate. Inflation also flattens space, like pulling on the corners of a crumpled sheet. The more you stretch it, the flatter it appears. Just as a balloon, when inflated enough, starts to look like a flat surface to an ant walking on it. The universe becomes increasingly flat as it inflates. So, the flatness problem is solved too. And what about those pesky magnetic monopoles? Well, if they were produced before inflation, they would have been diluted to near nothingness during the rapid expansion, spread so thin that they'd be almost impossible to find. Problem solved once again. Inflation then acts like a kind of cosmic prequel. It happens just before the hot, dense universe we associate with the Big Bang. You might even think of the traditional Big Bang as the after party, the moment when inflation ends and all the energy stored in the inflating field is released in a burst of heat and light. This is called reheating. And it's the point when the universe becomes filled with particles and radiation set in the stage for stars, galaxies, and everything else. So, what sparked this period of rapid expansion? The short answer is we're not entirely sure, but we have some compelling ideas. Inflation is thought to have been driven by a kind of field similar in concept to the fields we discussed earlier in quantum theory. This hypothetical field is called the inflaton field, and like other fields in physics, it has an energy associated with it. Imagine the inflaton field as a ball sitting on a hill. While it rests near the top, its energy remains nearly constant, enough to drive the exponential expansion of space. But eventually, the ball rolls down the hill. As it does, inflation ends, and the stored energy of the field is converted into particles and radiation. The universe becomes hot. Time begins to tick in the way we understand, and what we usually call the Big Bang gets underway. It's a beautiful idea, one that turns a chaotic birth into a graceful unfolding. But as always, it raises more questions. For example, what existed before inflation? Was there a pre-inflationary state, a vacuum, a quantum fluctuation? Was inflation itself eternal, spawning countless bubble universes in an endless cosmic froth? Some models suggest exactly that, a process called eternal inflation, where inflation never really ends, but continues in other regions, creating an infinite multiverse of pocket universes. Each bubble could have its own physical constants, its own dimensions, even its own concept of time, as just happens to be one that slowed down enough to allow stars, planets and sleepy scientists to emerge. And what about the inflattened field itself? Where did it come from? Was it always there? Did it emerge from a deeper set of laws? Or is it a temporary feature, like a ripple in a deeper ocean of reality? We don't know yet, but we're looking. Observations of the cosmic microwave background, the faint glow from the early universe, are helping us search for clues. Tiny fluctuations in that glow which inflation predicts have already been seen. They're like fingerprints left behind by the earliest moments of cosmic expansion. And maybe, just maybe, we'll find more evidence that inflation happened, or even hints about what came before. For now, cosmic inflation remains one of the most elegant, powerful, and mind-expanding ideas in science. A moment of near infinite speed and silence in which the universe didn't explode into being, but inflated into potential. Not a bang, not a flash, but a breath. Deep, fast, and utterly transformative. A silent boom that gave us the space to exist. Imagine for a moment that the universe, our entire vast and expanding cosmos with its billions of galaxies and glittering stars, is just one tiny bubble in an endless cosmic foam. One pocket of space among countless others, each with its own laws, histories, and possibilities. It's a humbling, almost dizzying idea, but according to a theory known as eternal inflation, this may be exactly what reality looks like on the grandest of scales. Tonight, we're going to float calmly through this vast and mysterious idea, a universe of universes, a multiverse born not from a singular explosion, but from a quiet, endless process of cosmic bubbling. A process that, if true, would mean that the idea of nothing may never have existed at all to begin. Let's return briefly to the theory of cosmic inflation, which we visited in the last chapter. Inflation proposes that the early universe underwent an incredibly rapid expansion, driven by the energy of a special field. This expansion smoothed out space, solved several cosmological puzzles, and set the stage for the hot Big Bang that followed. In the simplest versions of the theory, inflation is like turning on a fire hose. It blasts out a universe-sized patch of space, then turns off, and the universe evolves from there. But in the more nuanced and frankly more intriguing versions of the theory, inflation doesn't stop everywhere. In fact, it can't, because quantum fields are not perfectly smooth or predictable. There are tiny fluctuations in the inflating field from place to place. In some regions, the field might drop in energy and inflation ends. That's where a universe like ours begins. But in other regions, the field might remain high and inflation continues. Those regions expand faster and faster, outpacing the regions where inflation ended. And while universes like ours stop inflating and cool into stars and galaxies, the space between them keeps growing. This leads to a self-replicating runaway process, eternal inflation. Think of it like boiling water in a pot. As it heats, little bubbles form and rise to the surface. But imagine that instead of the bubbles popping and disappearing, they became their own separate worlds. Now, imagine that the boiling never stops. More and more bubbles form endlessly, each one expanding and evolving in its own way. That's the multiverse, as imagined by eternal inflation. Each bubble in this cosmic stew represents a universe. Some might be similar to ours. Others might have different physical laws, different particles, different forces, perhaps even different numbers of dimensions. In one bubble, gravity might be weaker. In another, stars might never form. In yet another, Space might curve back in on itself like a sphere. The variety could be endless, and here's the truly staggering part. This bubbling isn't just vast, it's eternal. Because in the regions where inflation doesn't stop, space keeps expanding exponentially. The faster it expands, the more room it creates for new bubbles to form. These bubbles are isolated from each other, separated by ever-growing expanses of inflating space. They can't interact. They might never even know about one another. But together, they form what's sometimes called the inflationary multiverse. An infinite landscape of universes born not from nothing, but from a process that never stops. So what does this mean for the idea of nothing? Well, it may suggest that nothing, true, absolute, total nothing, never existed. There was never a blank slate, a moment of perfect stillness before something emerged. Instead, there's always been something happening somewhere. A bubbling, stretching, inflating cosmos branching out forever in this picture. Our universe didn't arise from a singular beginning. It was just one of countless nucleation events where a region of space exited inflation and began evolving in the way we're familiar with. That means the Big Bang, as we know it, wasn't the beginning, just our beginning. Now, this might sound like science fiction, or at the very least wildly speculative, and to some extent it is speculative. We don't have direct evidence of other bubbles. We can't peer into other universes to confirm their existence. But eternal inflation isn't just a fantasy someone scribbled onto a whiteboard. It's a natural mathematical consequence of certain inflation models that fit very well with what we do observe, especially in the cosmic microwave background. It also ties in with other branches of theoretical physics. For example, in string theory, a framework that attempts to unify all the fundamental forces. There isn't just one solution for the shape of reality. There may be a landscape of possible configurations, each with its own unique set of laws. Eternal inflation could be the engine that explores that landscape, bubbling off new universes to try out each possibility. Some physicists even argue that this helps explain something very strange about our universe, why its physical constants seem so finely tuned for life. Gravity, electromagnetism, the masses of particles. If any of them were just slightly different, complex matter might never form. Planets might not exist. Chemistry wouldn't work. No stars, no life, no sleepy science videos. But if there are countless universes, each with slightly different properties, then it's not so surprising that at least one ours happens to have just the right ingredients. It's not that we're lucky. It's that we're in the one place where observers can exist to ask the question. This idea is sometimes called the anthropic principle. It doesn't mean we're special, just that our presence tells us something about the kind of bubble we happen to live in. Now, understandably, not everyone loves this idea. Some scientists find the multiverse unsatisfying because it seems hard to test. If we can never observe the other bubbles, can we really call this science? Is it philosophy wrapped in math? That's a fair criticism, and one the scientific community continues to debate, but there are efforts to find indirect clues. For example, some theories suggest that if two bubble universes ever bumped into each other, like soap bubbles in a sink, the collision might leave a mark in the cosmic microwave background. We haven't seen such a mark yet, but researchers are looking. Others explore whether quantum gravity or string theory might one day predict specific patterns that confirm the multiverse. For now, though eternal inflation remains a beautiful, compelling, and speculative extension of our best cosmological models. So, where does this leave us? It leaves us with a new way of thinking about everything, not as a singular event in a pre-existing void, but as one chapter in a never-ending story. A story that's been unfolding forever, not in time as we know it, but in the boundless potential of space itself. In this view, nothing becomes a kind of illusion. There is always something, a field, a fluctuation, a slow, eternal bubbling. It's a quiet, expansive idea that the cosmos has no beginning and no end. Just an endless generation of possibilities branching and inflating like foam in a never-emptied kettle. And somewhere in all that infinite froth, there's us. One bubble with just the right balance. One flicker of light in an endless ocean of possibility. Perhaps the question isn't why there is something rather than nothing, but rather why we're in this something. Why this bubble with these laws, with this calm patch of sky and this delicate moment of awareness rose from the quiet sea of the multiverse. It's the kind of thought that doesn't demand an answer, just wonder. And in that wonder, the bubbling continues. Let's take another deep and gentle breath and consider one more way the universe might have begun, or perhaps not begun at all. We've talked about tunneling from nothing. We've drifted through cosmic inflation and floated in the sea of the multiverse. Now, let's visit another elegant idea, one that doesn't just stretch space but bends time itself into a new shape. This is the idea of the cyclical universe, sometimes called the Big Bounce. It's a concept that suggests our universe may not have been born once, but over and over again in an eternal rhythm of expansion and contraction, bangs and bounces, a cosmic heartbeat that never stops. It's a soothing thought in a way that instead of a single dramatic beginning, there is a quiet pulse behind everything, an eternal inhale and exhale of creation. To understand the Big Bounce, let's go back to the traditional Big Bang model. In that model, the universe starts from a singularity, an infinitely dense point where all known physics breaks down. But singularities are deeply troubling to physicists. They signal a place where our theories stop making sense. Many scientists would prefer a model that avoids them, a model that explains the beginning without running into infinities. The Big Bounce is one such idea. Instead of a singularity, the Big Bang could have been the rebound from a previous contracting universe. Imagine the cosmos slowly collapsing under its own gravity. Galaxies drifting closer, stars merging, matter compressing, until the universe reaches a point of maximum density. But instead of ending in a final crunch, quantum effects cause a reversal. Space rebounds, expanding outward again in a new Big Bang. Expansion follows, then perhaps contraction again in an endless cycle. No beginning, no end, just a series of bounces. This idea isn't just poetic. It has mathematical backing in several models of quantum gravity, particularly loop quantum cosmology, a branch of physics that tries to unite Einstein's theory of general relativity with quantum mechanics. In loop quantum cosmology, space-time itself is thought to be woven from tiny, discrete loops, like a fabric of threads at the smallest scale. These loops can resist being squeezed into a singularity. Instead, when the universe becomes extremely dense, the quantum geometry pushes back, creating a bounce. In this picture, the Big Bang was not the beginning of time, but a transition, a bounce from a previous phase. The arrow of time continues smoothly through the bounce, like a pendulum swinging back and forth. What's more, this could mean that our universe carries subtle imprints of the one that came before. Some physicists are exploring whether traces of a previous cosmos might be visible in the cosmic microwave background, tiny patterns that could hint at a history older than the Big Bang itself. There are other cyclical models too. Some, inspired by string theory, suggest that our universe might be just one of two brains, giant sheets of space-time floating in higher dimensions. Every so often, these brains collide, unleashing energy that looks to us like a Big Bang. After drifting apart for billions of years, they attract each other again, collide again, and the cycle repeats. In this view, the universe is eternal, with bangs and bounces occurring endlessly as part of a higher dimensional dance. Each collision creates a new phase of cosmic history, wiping the slate clean but continuing the story. Still other models propose that dark energy, the mysterious force accelerating the expansion of the universe, might one day slow and reverse, pulling everything back together for another bounce. The details differ, but the theme is the same. The universe may be cyclic, an eternal return rather than a one-time event. Now, what does this mean for our question about nothing? If the universe truly bounces or cycles, then there may never have been a moment of nothingness at all. Instead of a sharp beginning from emptiness, the cosmos may be eternal in both directions of time, stretching back through infinite cycles of birth and death. Nothing never gets a turn on the stage. There is always something, always a universe expanding, contracting, rebounding. This is comforting in its own way. It sidesteps the troubling question of how something could come from nothing, replacing it with the idea that something has always been, changing form but never ceasing. The Big Bounce doesn't answer every mystery, of course. It still leaves us wondering why the laws of physics exist in the first place, why quantum geometry resists singularities, or why brains would drift and collide eternally. But it does give us a model of the cosmos without singular beginnings, without absolute nothingness, and perhaps more importantly, it gives us a new way of seeing our place in the universe. If the cosmos has cycled endlessly, then everything we see around us, every star and galaxy, every moment of time, is part of a rhythm older than imagination. Our existence is woven into a cosmic heartbeat, one beat among countless others. It makes the present moment feel both fragile and eternal, fleeting and infinite. And as you let your thoughts drift toward sleep, you might imagine the universe itself breathing, expanding, contracting, pausing, and beginning again. A gentle rhythm with no first breath and no final sigh. Just an endless, soothing flow of being. So far, we've wandered through several possibilities for the origin of the universe. We've tiptoed through quantum fluctuations, tunneling from nothing, cosmic inflation, eternal multiverses, and bouncing cycles. Each one gives us a different lens on the question, and each one shifts what we mean by nothing. But now, let's explore another perspective, one that doesn't come from physics equations, but from the way we use language and thought itself. What if nothing isn't a physical state at all, but a concept, a word that tricks us into imagining something impossible? Philosophers have wrestled with this question for centuries, and some have argued that true nothingness is not only non-existent, but incoherent. That it's not just that nothing never was, but that nothing cannot be. Think about it this way. When we say there's nothing in the fridge, we don't mean the fridge has vanished. We mean it's there, just empty of food. When we say nothing is happening, we don't mean the universe has ceased to exist. We mean nothing of interest is occurring. In everyday life, Nothing always refers to the absence of some specific thing, but not the absence of everything. So when we stretch that word to mean absolute nothingness, the total absence of space, time, matter, and laws, we may be pushing language beyond its limit. It's like trying to imagine a square circle or a married bachelor. The words sound like they describe something, but when you unpack them, they dissolve into contradiction. Some philosophers argue that's what we're doing when we talk about nothing. We're creating an illusion of meaning where none exists. Martin Heidegger, the German philosopher we mentioned earlier, framed the question this way: why is there something rather than nothing? He believed that asking this question opened a window into the deepest mystery of being. But others have responded by saying that the question is malformed, that nothing isn't a real alternative to something, so there's no sense in asking why something exists instead. To exist is to be. Nothingness isn't an option on the menu. Jean-Paul Sartre, the French existentialist, wrote a whole book called Being and Nothingness, where he suggested that nothingness is not a substance or a state, but a product of consciousness. When we become aware of what isn't, when we notice an absence, that's when nothingness appears. It's not out there in the cosmos waiting to be found. It's in here, in our minds, as we navigate the difference between what is and what is not. If that's true, then nothing is not the opposite of something. It's a shadow cast by thought itself. The universe never had to overcome nothing to exist. Nothing was never in the way. Instead, existence just is, and nothing is a word we invented to mark absences within it. This view may feel less satisfying than grand cosmological theories. It doesn't give us a bouncing cosmos or a bubbling multiverse, but in its own quiet way, it offers peace. It tells us that the burden of explaining how something came from nothing might be misplaced. There never was nothing. There always was being, and the only reason we think otherwise is because of the peculiar tricks of language and thought. In this way, nothing is not a cosmic mystery, but a linguistic one. It's not a question of physics, but of semantics, and maybe that's okay. Maybe part of the wonder of being human is that we invent impossible questions, just so we can marvel at the impossibility. Of course, this doesn't mean the scientific models we've explored are meaningless. Far from it. They help us understand the earliest moments of the universe as far as our physics can reach. They show us how space, time, matter, and energy behave near the limits of knowledge. But they also remind us that our words like nothing, beginning, cause our human tools. They evolved to help us find berries, track seasons, and tell stories. They're not always fit for probing the deepest structures of reality. So when we ask about nothing, we may be asking a question that's not just hard to answer, but impossible to phrase correctly. And yet, there's beauty in the asking, because it's in these edge cases of thought that we glimpse the limits of our own understanding. It's where we find wonder not only in the stars, but in the act of questioning itself. So what is nothing? We've seen it's never truly empty. It's quantum foam. It's a false vacuum. It's a fluctuation waiting to become. Or it's a cycle with no beginning and no end. Or it's a linguistic illusion, a shadow of being. Each answer is both satisfying and unsettling. Each one opens new doors, even as it closes old ones. And maybe that's the real gift of nothing. Not as a final explanation, but as a perpetual invitation. An invitation to wonder, to dream, to imagine. As you lie there drifting into sleep, you don't need to solve the question. You don't need to decide whether nothing exists or doesn't, whether the universe tunneled, bounced, or bubbled. You can simply rest in the quiet space the question creates. A space of possibility where thoughts float like stars across the night sky. Because sometimes the most comforting thing isn't the answer. It's the question itself, softly glowing in the dark. And so, as we reach the end of this gentle journey, let's let go of nothing. Let's let go of everything. Let's just breathe in the mystery of being here at all. Whether the universe emerged from a fluctuation, a bounce, a cycle, or no cause at all, the fact remains. Here we are, thinking, breathing, wondering. Something exists, and we are part of it. That truth is enough. Enough to fill the heart with quiet awe. Enough to ease the mind into stillness. Enough to drift with into dreams. So tonight, as you settle deeper into your pillow, remember that the universe is not asking you to solve it. It's simply offering you a place within it, a place of quiet wonder. You are part of the story, whether that story began in a bang, a bounce, a bubble, or no beginning at all. You are the stardust that dreamed of stars. You are the question asking itself. You are the something that wondered about nothing, and that's enough. Let the mystery hold you, like gravity holds the earth, like space holds the stars. Let the questions drift by like constellations, some familiar, some strange, all of them shining softly. Because the universe isn't only out there in distant galaxies or quantum fields. It's also here in your breath, your heartbeat, your thoughts as they slow and soften towards sleep. There is no rush to understand, no deadline to solve the riddle of nothing. Only this moment, this quiet, fleeting, eternal moment. And maybe, just maybe, that's all there ever was. Good night, fellow traveler in the cosmos. May your dreams be full of stars, and may nothing disturb your rest. Part 10. Imagine, just for a moment, that everything you see, feel, and experience the stars in the sky, the ground beneath your feet. Even the thoughts in your mind are not the ultimate reality, but the output of some deeper code. A simulation. This might sound like the plot of a science fiction film, but it is also a hypothesis that serious philosophers and physicists have considered. Could our universe itself be a simulation, a vast digital construct running on some unimaginable computer in a higher reality? Tonight, let's drift gently into this curious possibility, not with urgency or fear, but with calm curiosity. Because whether or not the universe is simulated, the wonder it inspires is very real. The idea gained modern attention from philosopher Nick Bostrom, who in 2003 published a paper suggesting that at least one of three propositions must be true. First, that civilizations never reached the level of technology required to run universe-scale simulations. Second, that even if civilizations reach that level, they are not interested in running such simulations. Or third, that if they do run simulations, then simulated beings like us would vastly outnumber real ones, making it likely that we ourselves are in a simulation. It's a neat trilemma, one that doesn't prove we're simulated, but that makes the possibility hard to dismiss entirely. And it touches on something deeper, the nature of reality itself. If our universe is simulated, then what we call physical laws may just be the rules of the code, consistent and reliable but not fundamental. The true reality would be whatever realm the simulators inhabit. Now, let's soften this idea a little. Because even if we were in a simulation, what difference would it make to our day-to-day lives? The stars would still shine. the earth would still turn, your tea would still taste warm, and your pillow would still feel soft. Whether atoms are made of quarks or of code, they still build the world we experience. In that sense, the simulation hypothesis may change our perspective, but not our lived reality. It may inspire awe, but it doesn't erase the beauty of a sunset or the kindness of a smile. Still, it's worth exploring what such a model would mean for our big question. Could nothing ever exist? If the universe is a simulation, then perhaps there was never nothing in the absolute sense. There was always some higher-level reality, some computer, some programmers, some substrate in which the simulation runs. In this picture, nothing is impossible because behind the apparent emptiness of our universe lies the fullness of another. And yet, even this only shifts the question. If we are simulated, then what about the reality of the simulators? Did their world emerge from nothing, or is it simulated too? Could there be layers upon layers of simulations, turtles all the way down? It's a dizzying thought, but one that shows how slippery the idea of nothing can be. Even when we think we've reached the bottom, there may be another level beneath. Some scientists dismiss the simulation hypothesis as untestable, but others have suggested ways it might leave traces. If our universe runs on a discrete digital substrate, then perhaps at the smallest scales, the smoothness of space and time might reveal tiny pixel-like granularity. Or maybe there are limits to the energy of particles, boundaries set by the resolution of the code. So far, we haven't found such signs, but the search continues. And even if we never find proof, the hypothesis invites us to think differently about reality. It reminds us that what we call fundamental may be contingent, that what we see may not be all there is. For our journey tonight, the simulation idea is less about proof and more about perspective. It shows us another way in which nothing might be an illusion. If we are simulated, then there was always something the simulator. If the simulator is simulated, then there was always something deeper still. Nothing never gets a chance. The chain of being stretches on, perhaps infinitely, leaving no room for a final void. Whether this comforts or unsettles you is a matter of temperament, but in the quiet of the night, it can be simply another reminder that existence is rich with possibilities. And in that richness, there is wonder. Whether real or simulated, whether ultimate or layered, the fact that we are here, thinking these thoughts, is astonishing enough. So where does all this leave us? We've explored the vacuum that isn't empty, the bounce that never ends, the bubbles that never stop forming, and even the possibility that all of it is running on someone else's computer. Each model gives us a different story about the beginning or the lack of one. And yet, no matter how many theories we consider, one thing keeps reappearing. Nothingness, in its purest sense, always seems to slip away. It hides behind language, behind physics, behind thought itself. The moment we try to pin it down, we find something else in its place. A field, a law, a fluctuation, a simulator. Something always emerges from the shadows, and perhaps that's the real answer. That nothing is not a physical state we might discover, but an idea that guides us toward deeper understanding. When we ask about nothing, we are really asking about the limits of our own concepts. We're stretching thought to the breaking point, asking it to imagine its own absence. And in doing so, we confront not only the mystery of the universe, but the mystery of mind. This makes the question of nothing less about cosmology and more about being human. Because what other creature asks such things? What other being lies awake at night, staring into the dark, wondering whether the dark itself exists? To ask about nothing is to glimpse the strangeness of our own existence. We are beings who can imagine what isn't, and in that imagination, we find both confusion and wonder. So why does this question matter? Why should we care whether nothing ever existed? Because it changes how we see everything. If nothing is impossible, then existence is necessary. It means that being is not a fragile accident, but a constant, eternal presence. If nothing never was, then something always will be. That's a strangely comforting thought. It suggests that reality is not precarious, perched on the edge of a void, but fundamental. That even in its quietest, simplest form, existence endures. On the other hand, if nothing were possible, if the universe could truly have come from an absence, then everything we see is even more miraculous. Every star, every atom, every thought becomes a gift without precedent, a spark out of absolute darkness. In either case, whether nothing is impossible or whether it gave way to everything, the result is awe. Wonder that we are here at all, suspended in the vast fabric of being. The ancient philosophers knew this feeling well. Parmenides argued that nothing cannot be, that only being exists. Democritus imagined atoms moving in the void, a kind of halfway nothing filled with motion. The mystics spoke of creation ex nihilo, out of nothing, not as a scientific description, but as a mystery of faith. And in our own time, physicists and philosophers still circle the same question, with new tools but the same unease. We may never agree on the details, but the persistence of the question tells us something. It tells us that nothing is one of the deepest mirrors we can hold up to ourselves. In wondering whether nothing ever was, we discover how strange it is that we are. We confront the fact that the universe could have been otherwise or not at all, and that recognition deepens the beauty of everything around us. So, as you let these thoughts settle, remember that the question of nothing is not a puzzle to solve before bed. It's a lullaby of wonder. It's a soft reminder that the universe is vast, that our knowledge is partial, and that mystery is not the enemy of understanding, but its companion. You don't need to know whether nothing ever existed. You only need to rest in the fact that something does. The sheets against your skin, the rhythm of your breath, the stars overhead, these are enough. And in their presence, the shadow of nothingness becomes less frightening. It becomes a backdrop against which being shines more brightly. Because maybe the point was never to answer the question, but to feel its weight, and then to let it go. Let's drift one last time into the heart of the question. What have we really been asking all along? At first it seems simple. Could there ever have been nothing? But as we've seen, the deeper we search, the more nothing turns into something. A vacuum becomes a quantum field. An absence becomes a fluctuation. A before becomes a bounce. Even language itself betrays us, sneaking in assumptions of being whenever we try to talk about its absence. And yet, the question persists. We cannot quite let it go, because it touches something fundamental in us. To ask about nothing is to ask why there is anything at all. Why we are here, drifting through this strange, luminous universe, able to wonder in the first place. Some philosophers suggest that the question is unanswerable, not because the universe hides its secrets, but because the question itself doesn't make sense. If nothing were possible, there would be no one to notice. The very act of asking proves the reality of something. It's a paradox we can never escape. Others think that's precisely why it's the deepest of all questions, because it brings us to the edge of what thought can do. It's not just about cosmology or physics. It's about the limits of language, imagination, and reason. To sit with the question of nothing is to practice humility. It is to admit that we are small creatures in a vast cosmos, glimpsing mysteries too big for our categories. And yet, in that humility, there is peace. We don't have to solve everything to feel wonder. We don't have to grasp the whole to love the part. So, what do we carry with us from this long, slow journey? First, the reminder that the universe is richer than it appears. What looks like emptiness is full of structure. What feels like silence hums with hidden music. What seems like nothing may be the deepest kind of something. Second, the recognition that our questions are part of the universe too. The fact that matter can dream of meaning, that atoms can ask why, is itself a miracle. The universe is not only galaxies and laws, but also thought and imagination. And finally, we carry the comfort that whether nothing ever was or not, something is here now. This moment, this breath, this awareness. That's enough. Think of the night sky again. Countless stars, some already gone but still shining across time. Vast darkness between them, which is not empty at all, but woven with invisible threads of energy and possibility. You are part of that tapestry, not outside it, not separate from it, but within it. Whatever the origin, whatever the fate, you are a child of this cosmos. The same laws that govern galaxies shape the rhythm of your heartbeat. The same particles that flicker in quantum foam shimmer in your thoughts. To be alive is to be woven into the greatest mystery there is. And to ask about nothing is, in the end, just another way of saying thank you for being here at all. So now, as your eyes grow heavier, let the question dissolve into silence. You don't need to hold it anymore. Let it go like a leaf drifting downstream. Let the stars of thought dim one by one until only the quiet glow of being remains. Rest in that glow. Rest in the something that is. Rest in the peace of not needing answers. For tonight, it is enough to breathe, to wonder, and to sleep. Tomorrow, the universe will still be here. Tomorrow, the questions will still shine. But for now, you can close your eyes and drift, knowing that whether nothing ever was or not, you are something. And that is the greatest wonder of all. _stop HERE. Part 13. Eon D before we close our eyes fully. Let's take one last quiet detour. Because the question of nothing is not just about physics or philosophy. It is also about meaning. Why does it matter to us? Why do we care whether there was ever nothing or whether something is eternal? The stars don't seem to mind. The galaxies spin whether or not we understand them. Yet we, fragile humans, are compelled to ask. And that reveals something profound. Our search for nothing is really a search for belonging. We want to know where we fit, what our place is in this grand unfolding. If nothing ever was, then our existence is a fragile spark in the dark. If nothing never was, then we are part of something eternal. Either way, the question reaches into our hearts as much as our minds. There is comfort in both directions. If nothing ever was, then everything is a miracle, every breath a gift born from absolute absence. You are here against impossible odds, and that makes life precious beyond measure. If nothing never was, then you are eternal matter, eternal energy, eternal being taking temporary form. You are part of something that cannot be erased, only transformed. That too is comforting. In both views, the ordinary becomes extraordinary. The glass of water at your bedside is either stardust forged in ancient suns or a gift drawn out of nothingness itself. Either way, it glows with meaning. To ask about nothing is to see the sacred in the everyday. Perhaps this is why the question has never left us. It appears in myth and religion, in poetry and science, in quiet late-night thoughts, and in the most advanced equations. Each generation asks again, and each finds new language for the same mystery. Creation stories speak of gods shaping order from chaos or calling the world from the void. Philosophers frame the paradox in careful words. Physicists measure fluctuations in the cosmic microwave background. But underneath it all is the same human wonder. Why is there something rather than nothing? And maybe the point is not to answer once and for all, but to keep asking. To let the question renew our sense of awe again and again. So tonight, as you rest, remember that nothing is not a threat. It is an invitation. It invites you to see how precious being is, how fragile and how resilient. It reminds you that existence is not guaranteed. And yet here it is, filling your lungs, lighting the stars, humming in every atom. It teaches us humility because we cannot grasp it fully, and it teaches us gratitude because we don't need to. We can simply live, breathe, wonder, and rest. Whether the universe began in a bang, a bounce, a bubble, or a line of code, the fact that it Baganor always was is enough. So let go now. Let go of the questions. Let go of the search for certainty. Let your thoughts dissolve like mist at dawn. Let your breath slow and deepen. The universe is vast and patient. It doesn't demand your answers tonight. It offers only the gentle gift of rest. Take that gift. Close your eyes. Feel the weight of your body sink into the bed, held like a planet in gravity. Feel the stillness gather around you like a blanket of stars. You are safe. You are part of something. And in this moment, that is all that matters. Good night, traveler. May your dreams be wide as the cosmos, soft as starlight, and full of the quiet wonder that nothing and everything brings.